Hey everyone, I'm Erica, and this is my colleague Ahmet. We are machine learning engineers at the AI Institute, and we're super excited today to present our end-to-end robotics ML training platform with Ray. So today we'll be going over some background on the AI Institute, robot learning and the challenges associated with it, our training platform solution, and we'll go over some major design choices we made. And Ahmet will be showing a demo that showcases a lot of the features of our platform. So to start off with, the AI Institute is a research institute, and our mission is to solve the most important and fundamental challenges in robotics and AI. We're really focused on longer-term problems and making a more lasting impact in the field. And in terms of the machine learning portion, we're focused on two big areas. One is what we call athletic intelligence, and that means giving robots dexterity, giving them the ability to manipulate things and navigate rooms and different environments, and also cognitive intelligence, so helping robots really understand the world they live in. This is through work that includes foundation models, task and motion planning, and associated projects like how do we collect bigger and better data. So at the AI Institute, we have a growing team of ML engineers, and our job is to help accelerate this research. And we do so by building platforms and tooling that really help scale up models and data that are used for these projects. So I wanted to first start off and motivate the talk by kind of showing one end result of our platform. So here you can see there's a policy deployed on a Boston Dynamics spot robot. You can initialize, so you can have the spot start in many different start positions, but it's able to detect where this bike seat is and extract it from the shelf. So what is the machine learning model behind this kind of work? This is something called robotics imitation learning. And imitation learning is learning from demonstration. So one kind of imitation learning is called behavior cloning, where you learn a policy directly from the input and output data with supervised learning. I'm sure all of you have heard of LLMs. They're actually one really famous example of behavior cloning, of course with other reinforcement learning that happens afterwards. If you think about LLMs, it's actually a sequential decision-making problem. So every token prediction affects the next token prediction. And in robotics imitation learning, instead of predicting tokens, we're predicting actions. And similarly, one action prediction affects the next action prediction. Robotics imitation learning is actually a very, very difficult problem if you think about how it compares with LLMs. One way to think about it is, what's the difference between predicting actions and predicting language tokens? Well, actions are actually in this continuous space, while language tokens are discrete. Also, when you have a robot operating in the real world, there's just a lot of stochasticity from the environment. There's a lot of randomness, and you don't get this type of randomness in LLMs. So it's actually a much more difficult problem. In the last slide, I showed the video of the spot robot, and that's actually one example of a visiomotor policy, which essentially means control from pixel. So the spot has a camera on it, and it's taking images of what it sees, and this image is fed into an encoder. The encoder produces an embedding vector, and along with the state vector of the robot, this is input into a policy, and the policy outputs an action. One kind of more tangible example of this is in autonomous driving. So the cars can have cameras, and they'll see the road. You pass it through a machine learning model, and the model tells you to steer right or left. So it's very similar to that. To do this type of machine learning, the full life cycle includes data collection, data processing, data training, distributed training, and deployment on the robot. There are some very unique challenges associated with robotics. One is, to do this training, you want data. And data collection in robotics is slow and expensive. So there's a lot of work in this area, but even some of the most recent work maybe gives you on the order of 100 demonstrations an hour. So it's very, very expensive. These robots also operate in these dynamic multi-actor environments, so you really want enough data to be able to compensate for that. Some people solve this problem by using simulated data, and that's a very good approach, but there is this sim to real gap. So it's not so simple as just generating a ton of simulated data and then being able to transfer that to the real world. There's still that gap there that is being worked on in this field. And lastly, we actually need to deploy these models on real robots. And so there are a bunch of resource constraints associated with that, which is another challenge in robotics. Today, we wanted to focus kind of on the middle section of this life cycle, so in the data processing and the distributed training, which Ray helps us a lot with. And lastly, I also wanted to mention our specific ML training challenges at the Institute. So one is we're a research institute. We have a bunch of different projects. We have many users using the same platform that we're building. So we want to make sure we have fair resource allocation, but no resource contention between the different jobs that are happening at once. We do have a shared GKE cluster that we're using. And so how to design that system was something we thought a lot about. And then also on the data side, our data is growing. It doesn't necessarily fit in memory. So how do we do that processing effectively? And at a research institute, the data is continually changing, the schema is changing, so how do you keep track of the different versioning and lineage? On the training side, as I mentioned, we have a bunch of different approaches, a bunch of different models, so we're trying to support a really wide range of projects, and we want people to have reproducible results. And lastly, something we'll go into more in this talk is in robotics, you can't do the normal train test split for validation that you can do normally in machine learning. So we actually wanted to integrate in our system this simulation evaluation. And that means being able to see how your current model is doing in a simulated environment and whether the robot can successfully perform the task or not. And we'll show a little bit more of that later. So to do this, we actually built a new ML platform we call Robotensors. And this is a Python API, and it kind of brings together many different components. So the compute infrastructure, the data, the training, the evaluation, and the deployment. And you can see here, you can bring in data from our data platform, where people are contributing to at the Institute. You can do this last mile data processing either online or offline, and pass it to the train module. In the train module, you can bring in your custom models, your custom configurations. It's automatically integrated with weights and biases. And you can also construct models that are built off of other models. So you can kind of piece together different models that other users have contributed. We built this model evaluation with simulation that we'll go into more later. And we also provide some debugging tools to help people figure out what's going on. And so these train and tune jobs are submitted to our Kubernetes cluster. And that's integrated with the weights and biases model registry. And we're planning to integrate that with the inference side to then directly deploy that to the robot. So we chose Ray because it's nice to have one framework that kind of spans all these different things we're trying to do. We use many modules in Ray. We use Ray Data, Ray Core, Ray Train, Ray Tune. Also, Ray offers a lot of flexibility, and I mentioned we are supporting many different types of research projects, so it allowed us to build something that is very flexible and many different people can use it. So I wanted to go into kind of two different design choices we made for this platform. The first one, I think if you all have been using Ray, you know it's not recommended to do multi-tenant RayClusters. And as I mentioned before, we have a bunch of different users. And we have the shared infrastructure. So how do we actually manage that so that all these users can use this shared infrastructure? And the way we did that is kind of by dividing into these dev clusters and a production queue. So dev cluster is something where any user can launch their own RayCluster. That RayCluster is theirs. It is always available. But the trade-off is it's a smaller cluster. You won't get as many expensive GPUs, but it's really meant for you to iterate really quickly on. So we want people to be able to do their model development, their debugging, and smaller scale training and validation. Once they're ready, they can then send these jobs over to the production queue. And now they can request the expensive GPUs. They can really scale up their training job. But on this side, we're launching a transient Ray cluster. So the Ray cluster spins up, it runs a job, and once it's done, it can terminate. And so that's how we manage to be able to solve this multi-tenant problem and still support many, many users. And the other part I wanted to highlight is the simulation evaluation. So as I mentioned before, this is really unique to robotics where we want to have physical simulation in the loop. And we wanted to be able to auto-scale this part independently from the training. Because the simulation evaluation, it can happen on cheaper GPUs, even CPUs. We don't need to do it on the expensive training nodes. We wanted to isolate the resources and the processes from the training, so the training is not affected by this. And we wanted to not block the training. So if someone decides to do training versus training and the simulation evaluation, we want the training side to be the same. So this is where we felt Ray really shined for us. We were able to basically have different resource types. So we have these data nodes that are doing the data preprocessing. We have the train nodes doing the training part, and then we have sim nodes doing the simulation evaluation. And during training, after every n epochs, we actually have this callback system where the current model is sent over to the simulation nodes. And then we have the simulation actor manager that starts launching all these simulation evaluation jobs. And once it's done, the results are all sent back to weights and biases, so you can see them side by side. You can see your train loss, and then you can see, hey, did the robot actually complete the task in the simulation? This was very powerful, and on top of that, Ray also allows you to have different environments for different actors, and so we were able to run different types of simulation environments that have conflicting dependencies, which is very, very important. We actually spent quite a bit of time on this actor manager part because we actually run thousands of simulations per training run. And it's really easy to run into out-of-memory problems and how to schedule it so that you're getting the results back in a meaningful way was something we spent a lot of effort on. So now I wanted to pass it over to Ahmet, who will show a demo of our system.
I got it. Thank you. Thank you, Erica. Yeah, so in this part, actually, by the way, I'm Ahmet, and I'm also a machine learning engineer at the AI Institute. And on this part, we would like to do a demo of the features Erica was described. And it is basically focusing on a sample use case where we can basically give you the idea about what is actually is our development cycle looks like. So the content is going to be like, we are going to create our custom development RayClusters using our CLI tool for the researchers. We abstracted out the Ray cube like a cluster creation process. And we are going to train a diffusion policy model using Ray Train PyTorch Lightning. And we are going to do a deep dive into this experimentation process. And then we'll remove our development cluster. We are not going to be covering our production cycle, which is to submit larger scale jobs to the queue. This is also a work in progress and also a little bit beyond of the presentation time limit. So let's maybe go ahead of the first step, like creating a custom cluster for us for our demo. So let's go for the. Sorry, I need to open the YouTube link. It's better. Yeah, this is our CLI tool, Robotensors. Yeah, so there's some connection stuff, but now you're back. So using our tool, we have like different types of, it is simple as that. So you can create your cluster, update your cluster, and delete the cluster, and you can submit to that cluster. You can also use Ray's SDK or CLI as well in order to do that. But this is more abstraction. And for cluster creation, we actually like abstracted out, pre-configured all of our training and evaluation nodes, and also the data nodes over there. So the researchers can easily like call whatever the nodes they want to create, and they can easily onboard with that. So let's try to create a Summit demo cluster using like a 100 nodes, eight 800 nodes, and one simulation nodes that we call MimicGen replicas in our case. And let's see the creation progress. By the way, all lifecycle management of these cluster creation is handled by the Airflow in the background. So we are making sure that cluster is up and ready. And right now we are good to go. So let's go and try to submit a training job. So we have a custom training for doing this diffusion policy model. We will dive deeper on this one. But this is like, we have successfully submitted our training job to our Ray cluster that we just created. And let's do actually a little bit fast forward because training like needs time. So let's go 10 minutes later. And right now you are able to see your cluster utilization. Ray has a great UI. There's also other different types of dashboards available. You can also see the logs from the Ray UI, of course, but there's also like you can check where are you at the training using your Ray CLI, basically, just the job submission. So we already got the epoch 10, which means our evaluation started because we said that every 10 epochs we want to do evaluation. And this is our data looks like. So we said that this is a diffusion policy model, and it is actually using 12 different data task, like a robot task. And this is using a MimicGen data set, which is a benchmark data set for robotics to do train or evaluate your models or your imitation models and your RL models, basically. So the tasks are looking like, so I'm just showing the simulation videos to give you the idea. So there is pick and place tasks. A robot picks the objects and then place it in the other bin. There is like a stacking task. There is nut assembly. There is mock cleanup, coffee preparation. So all of the different tasks, and we are aiming to learn a single model that kind of like generalizes over all of these different tasks. And whenever it is prompted to do a single task, it should do that successfully. So these are what the data looks like. And actually, let's try to look at our cluster setup a little bit more. So in the cluster section, you can see like we already scaled up 20 pods for the simulation, and there is one pod that is actually doing the training. You can see like the training node easily over there, and the other nodes are actually doing the simulation, and this is not blocking the training that we are doing because asynchronous. So we can actually name our actors. So here you can actually see which actor is running and which task actor is running. So you can see this is running for epoch 4, hammer cleanup. There is like a coffee preparation and the other stuff. So you can actually keep track of what's going on in the cluster. So it's not really, black box that from the outside. So the model, when it comes to model, maybe I can talk a little bit about the model. So it is a diffusion policy, which is like a really effective model that, as Erika mentioned, there is this embedding. You basically just embed the representation of the model that you see. And this is doing an action prediction right now. But it is using a diffusion head, which is basically, model starts with the noisy guesses of the action, and it progressively improving that guess. And how it guess the action, the guess of the action is basically distributed over time. It learns that, and then this diffusion policy is actually conditioned on the robot's observation. So we are actually having a 2 camera here from this MimicGen data set. There is like a one from the robot arm and one from the seeing the scene basically overall, and this is how we can basically like train our model. And the output is basically really similar to what the expert would have performed. So here you can see there is a hammer cleanup. So the robot reaches out to the drawer. It opens the drawer, takes the hammer and put the hammer inside the drawer and closes the drawer. So it can do, if it can do that, it means success for us. So, but we are doing these evaluations asynchronously multiple times, and we are sending success rates back to our weights and bias tool. So you can actually see our success rates evolving over time. Sometimes it's going good, sometimes it is. You can see actually, am I overfitting it or not, basically. So there is a bunch of signals. Because usually imitation learning, you cannot do valid like a train test split and then just use your test data for evaluation per se. That's why the only proxy you would usually have is the training loss. And the only way that you can see if it is useful is like deploying it to robot. But that's a little bit expensive process. So we actually had a similar case we had like recently. So we were converging training loss really good as expected. But actually we couldn't get any success rate from the training. Our simulations were not actually like giving a good results for us. So we actually like when we were checking to understand troubleshooting this problem, we actually saw that there is a bug in our pre-processing logic, and on this bug, like we were skipping the first part of our episodes for some reason. It was a bug, and then the robots, like as we showed just earlier, its first task is to reach out to the drawer, not the hammer. But in here, it basically tries to almost all of the time. It tries to preferably reach to the hammer. And then this gives us the idea about, okay, so it learns something definitely, but it is learning on a wrong data set, basically. So that's how we can make sense and then fix our data set, basically, over there. So that's basically how we are doing our development for now. And for example, if your model is ready, everything is ready, you can basically submit to our queue and then do the large-scale hyperparameter sweep, or even if you test with the larger encoder, larger like a diffusion model or whatever model you want to test. So, and the stuff that we are right now working on are definitely with the queue integration we are working on. There is also like right now this experiment was on GKE, on Google Cloud, and we are working on expanding to the Lambda clouds, and we have also on-site cluster. And thanks to Ray's flexibility, it is really actually easy to move the cluster over the different providers over different Kubernetes environments. So which was really good. And we are also experimenting with the new features like the detached actors for caching some data. And actually, like yesterday, we learned about this ADAC feature that Ray is just creating right now. So we are also really excited about that, the augmented compiled graph stuff. So yeah, we will be really working on those for the next step. Yeah, so I think that's, before last but not least, let's just don't forget to close our cluster because they cost money basically. So let's go, and it is just easy to say, robust tensors, delete our resource, and then the resource will be removed. So that basically concludes our demo. It's a bit quick, but thanks for listening it. So we would like to also thank to our collaborators within the institute. We are working with the data engineering team, MLOps team, DevOps team, and also lots of collaborations with the researchers because we would like to get their experiment when they're doing the development. We are also hiring, so don't hesitate to reach out to us either after this meeting, either from the email, anything you want. And I think it is a good time for the questions right now. Thank you so much.
Go ahead.
So it's hard to see, but...
Yeah, I have a quick question. So you mentioned that you have different dependencies for different actors. Some of them have like conflicting dependencies. how are you managing them? Like, is it through Docker? Is it explicitly stating dependencies?
Yeah, so we have like different Docker images that have all the dependencies needed for that simulation environment. And then depending on which simulation it is, we have actors that use specific resources. So in Ray, you can say like, you have this worker group, and you can actually give it any label you want. So we say like, oh, this worker group is for the MimicGen benchmark.
Okay.
And then,
by the way, for the audience cannot hear the question, I just got a warning. So the question was about how we handle the dependencies of our actors that we have for simulation if there is different dependencies.
yeah. So then you can say, like when we have our specific MimicGen actor, we can say, hey, we request 1 unit of this MimicGen resource, and then it'll link to that specific worker group in Ray.
Yeah, I think I'll come to you. Go ahead, please.
How are you like streaming and storing your data? Like, are you like sending like tensors like over the wire, or do you have like some kind of special formats?
The question is about how to send the data to the training nodes.
Yeah, like, I'm sending data into training runs and then like yanking out for storage somewhere. Like,
Uh-huh.
like how's this going over the wire? Like, how how are you saving it? I'm just kind of curious.
Yeah, we are using Ray data occasionally. And basically, like the data is stored in our like a data platform, but it is technically either a HDF5 file or either a Parquet files that are located on the the GCS storage as a bucket. And depending on our configuration, because if it is on the different cluster, we need to transfer data there. And we have basically like using some automatic like data copiers over there in order to make sure like it has the repeatable like experimentation that we are doing. But it is using Ray data is actually really like helping us to get free from the handling with the data locality problem.
Can you talk more about like switching job to production? How is it different from the dev environment?
Yeah, so the difference between the dev and prod. So we are a research institute, so production is different than like industry production. Really, the production is like just to allow the users to request like more resources, so the expensive GPUs be able to scale up a lot, and to do that in a way that's fair, so that everyone can get a chance at using the resources. Yeah, but that's probably the biggest difference between the dev and the prod side. Yeah.
Can you go into more detail how you handle that?
Oh, so it's actually like a separate process. So Ahmet was showing like how you launch your dev clusters. You can see there. On the prod side, when you submit the job, you actually submit to a queue. And the queue will handle all of like launching that prod cluster, running that job, and terminating it. So it's like 2 different branches. Yeah.
Can I ask a follow-up to that? You mentioned the dev cluster. Is it per user? Each user gets their own cluster, and that's how you ensure fair sharing between the developers?
Yeah.
Yeah, please.
How was the learning curve when different Gundogdu features migrated to the Ray from the traditional?
Yeah, it's a great question. How was the learning curve, by the way? Repeating the question, how is the learning curve for the researchers to onboard this platform, right? So it is pretty, because it is flexible, so first of all, the researchers are really familiar with the Lightning, really familiar with the PyTorch environment already, and they are really good, they have really good familiarity with using Torch dataset. And here, we actually have ability to serve the data actually as a Torch loader. But if you have like a more scaled up stuff, we also have alternative version to use Ray data module. So we try to make it really like a less steps for them to onboard, so it can be embraced by them basically. So it's a difficult problem.
So you talk about like having 2 clusters. One is like the development cluster, production cluster, which is good. But how do you make sure that like not one job or one user is going to take all the resources that like the other jobs or other pieces
Yeah, that's like how do we make sure a user to get all of the resources that we have at a one time to submitting like a production job you're asking. It is basically handled by queue. So we can actually put different like policies based on our company, whether it could be like a priority for the users, could be priority based on the team, or priority or different like namespaces that we created over there. And then you can basically implement all logic there. And then, for example, if the cluster is empty, you can run your job, technically speaking, but then maybe higher priority person comes, it can kill your job. And then because you should wait, like if you have a checkpointing, everything set up, it shouldn't be like much problem unless the time constraints.
So to follow up, like if a higher priority job comes in, do you can't like kill the low priority job or you scale down the low priority job?
Yes, this is if the high priority person comes and kills the low priority job. It can actually we don't have a direct solution that I can tell right now. But right now we are starting to onboard people, so we haven't really got our limits that much. But I think that's the problem. Maybe we can answer better like next time if you're here.
Yeah, just to be clear, like the queue, we're using queue like K-U-E-U, so the Kubernetes queue system. So it's hard to know the difference when you're talking about it. So. Yeah.
There's a question I saw over there. Yeah.
So was there a need to, like, if you train a visual language action model, which is like a recent like foundation models for robotics, the entire data is almost the order of magnitude of terabytes. So with at least with typical LLMs, the data can sit on the same machine as the training. Was that a challenge, and how was it dealt with? I'm just curious.
Yeah, data loading is a big challenge, especially for working with the video types of data sets and lots of robot action sensors data. And technically, like, if you at that much scale that your data cannot be materialized to your like a memory or something like that, we always have a solution to stream the data, but also that comes with the other like a bottlenecks that your stream might be slower than your model iteration. So that's how you can basically like improve more on the network configurations, I guess. Yeah.
I'm curious about the training of the imitation learning models. Are you guys leveraging Ray's RLib, or do you guys have something in-house that you're using for the training of that?
Yeah, that's a good question. So for what we've shown, so the question was whether we're leveraging RLib. So for what we've shown, it's just pure supervised learning. So we are using the Ray train module. But there is, obviously a lot of reinforcement learning in robotics. So that's something we are planning on bringing into our platform. We're still evaluating whether RLib is the right tool, but it's definitely under consideration.
Yeah. Maybe we can get one or two more, and we are out of time. But we are happy to answer any questions afterwards. Maybe last one. You haven't really asked, so maybe you can.
I wanted to ask, how do you support the experimentation cycle if researchers make some changes here? That you mentioned there's like Docker images. How do you if they need to introduce new dependency, does that developer workflow involve rebuilding Docker images, or do you sync changes across the cluster?
Great question.
So how do you, and what is the development experience? Like when you make changes, you have to rebuild the Docker. So that's actually one of the reasons we love Ray, because they have different features. Like you can do PyModules, which actually will upload your most recent changes of that module to the cluster. So that means you can make changes and just submit the job, and your new code is there already. You can also do additional pip installations just through the runtime environment in Ray. And then that's good for just development. And then once you're sure, I want to include these dependencies, then you can build it into your Docker image. So avoiding this Docker building cycle was really huge.
Yeah, I guess, we should end the question part, but as I said, it will be we are happy to talk about any questions you have. So thank you for listening us. Hope the rest of the meeting.
Yeah, thank you.